In 1987, Detroit Diesel did the unthinkable by killing the engine that made them famous, and accidentally started the greatest rivalry in trucking history. That's when they introduced the Series 60, first appearing in buses and heavy-duty applications before reaching highway trucks by 1988. For nearly 50 years, the company had built its reputation on the distinctive whine of two-stroke engines, the Screamin' Jimmy that powered everything from city buses to long-haul trucks. But with the Series 60, they began phasing out the two-stroke legends that had defined the company, introducing a clean-sheet four-stroke design that represented everything Detroit Diesel had never been: quiet, fuel-efficient, and controlled by a computer. 300 miles south in Peoria, Illinois, Caterpillar executives were paying attention. The construction equipment giant had supplied on-highway engines since the 1970s, but hadn't rivaled Detroit's dominance in fleet trucks. The Series 60 changed that calculation. If Detroit could reinvent itself overnight, maybe there was room for a second player in the highway game. What followed was 23 years of the most intense rivalry in American trucking history. Not the superficial brand loyalty that sells t-shirts and bumper stickers, but a fundamental philosophical divide about what a diesel engine should be. Detroit believed in evolution, constant refinement, electronic integration, and adaptation to whatever regulations came next. Caterpillar believed in permanence, building engines so bulletproof that they'd outlast the trucks they powered, the companies that made them, and possibly the drivers who ran them. The Series 60 that launched this war was unlike anything Detroit had ever built. Where the old two-strokes fired on every revolution of the crankshaft, the Series 60 used a conventional four-stroke cycle. Where the two strokes relied on mechanical fuel injection that could be adjusted with basic tools, the Series 60 introduced DDEC, Detroit Diesel Electronic Controls, the first fully integrated engine management system in the trucking industry. The transformation was jarring for anyone who understood Detroit's DNA. Detroit initially offered the Series 60 in 11.1 liters, with the 12.7-liter version quickly becoming the standard choice for highway trucks in the early 90s, producing 350 to 365 horsepower in its initial highway configuration. But the real revolution was invisible. DDEC could automatically adjust fuel delivery, turbocharger boost pressure, and injection timing based on altitude, temperature, and load conditions. It was a computer making thousands of decisions per second that drivers had previously made by feel. The engine's architecture reflected Detroit's commitment to efficiency over tradition. The Series 60 used a cast iron block with wet cylinder liners, allowing for easier rebuilds while maintaining structural integrity. The single overhead cam design eliminated push rods and simplified the valve train while retaining rocker arms. Most importantly, the electronic unit injection system could deliver fuel at nearly 30,000 psi, exceptionally high for its time, and a key to its clean, efficient combustion. Fleet managers loved it immediately. The Series 60 delivered fuel economy that the old two-strokes couldn't match, often 6.5 to 7 miles per gallon compared to the 4.5 to 5 that were typical of mechanical engines. Fleet reports suggested downtime dropped significantly, often by half, thanks to easier diagnostics. By 1990, Detroit had sold over 100,000 Series 60 engines, capturing market share that had belonged to Cummins and International for decades. Caterpillar's response came in 1993 with the 3406E, the electronic evolution of their proven 3406 platform. Where Detroit had started fresh, Caterpillar refined what already worked. The 3406E displaced 14.6 liters through an inline-six design that produced between 425 and 600 horsepower, with torque ratings that reached 2,050 pound-foot, numbers that made the Series 60 look almost delicate by comparison. The engineering philosophy behind the 3406E reflected Caterpillar's construction equipment heritage. The engine block was cast from high-strength iron with thicker wall sections than typical automotive diesels. The crankshaft was forged from steel and heat-treated to withstand the shock loads common in vocational applications. Most critically, earlier 3406B and C engines used the peak hybrid system, but the 3406E moved to CAT's fully electronic ADEM controls. This system gave Caterpillar the best of both worlds, or so they believed. The mechanically actuated, electronically controlled unit injectors, MEUI type, could deliver fuel at up to roughly 24,000 psi while maintaining the simplicity that allowed field repairs with basic tools. CAT's ADEM electronic control system provided diagnostic capabilities while keeping the engine familiar and serviceable for mechanics used to traditional Caterpillar hardware. The 3406E represented Caterpillar's core philosophy: build it heavy, build it simple, and build it to last. The engine weighed around 3,000 pounds versus roughly 2,600 for the Series 60, but that extra mass translated into durability that became legendary among owner-operators. The 3406E used a two-valve cylinder head designed with larger water jackets and thicker deck surfaces to handle the thermal stress of sustained high-power operation. Detroit prioritized efficiency and integration, while Caterpillar valued simplicity and endurance. Detroit engines became the choice of large fleets that valued fuel economy, uptime, and standardized maintenance procedures. The Series 60's lighter weight meant better payload capacity, often 300 to 400 pounds more cargo per load compared to competitive engines. DDEC's diagnostic capabilities reduced the skill level required for basic troubleshooting, allowing fleet mechanics to identify problems without the years of experience traditionally required for diesel diagnosis. The electronic integration went beyond simple diagnostics. DDEC could communicate with transmission controls to optimize shift points for fuel economy, coordinate with engine brakes to provide seamless retarding, and even adjust idle speed based on ambient temperature and electrical load. This level of integration was revolutionary in an industry where engines, transmissions, and chassis had traditionally operated as separate systems. Caterpillar engines attracted owner-operators and smaller fleets that prioritized durability and repairability over efficiency. The 3406E could handle abuse that would destroy other engines: sustained operation at maximum power, poor fuel quality, extended service intervals, and the kind of neglect that was common in smaller operations. When it finally did need service, the work could be done with conventional tools by mechanics who understood diesel fundamentals rather than computer diagnostics. Both the 3406E and the Series 60 could reach 1,000,000 miles before major work in the hands of a careful owner, but Caterpillar built a reputation for heavier castings and stouter bottom ends that many operators trusted for repeated rebuilds. The rebuild process was straightforward enough that many owner-operators performed their own overhauls, something virtually impossible with electronically controlled engines that required specialized programming and calibration. The rivalry intensified in 1999 when Caterpillar introduced the C15, a 15.2-liter evolution of the 3406E that addressed some of the earlier engine's weaknesses while maintaining its core strengths. The C15 produced up to 625 horsepower and 2,050 pound-foot of torque, with improved sealing that reduced the oil leaks that had plagued the 3406E. The C15 featured electronically controlled unit injectors, EUI, driven by the camshaft, not hydraulically actuated systems. The C15's development reflected Caterpillar's response to Detroit's electronic advantages while maintaining mechanical fundamentals. The later C15 introduced a four-valve design that improved airflow and combustion efficiency compared to the 3406E's two-valve cylinder head. The injection system was refined to deliver fuel in multiple pulses per combustion cycle, reducing noise and emissions while maintaining the high-pressure delivery that CAT's engineers preferred. Detroit responded by expanding the Series 60 family with larger displacement variants and more powerful DDEC generations. By the early 90s, the 12.7-liter Series 60 had become available, offering increased power density for applications that required maximum performance within weight restrictions. DDEC 2 introduced more precise fuel mapping and improved diagnostic capabilities. DDEC 3 expanded cruise and engine brake control features. DDEC 4 refined electronic unit injection with higher precision, not introduced it. By 2000, the rivalry had split the trucking industry into two camps. Detroit dominated the fleet market with engines that prioritized efficiency and integration, Large carriers like Schneider National and J.B. Hunt standardized on Series 60 power plants because the electronic controls reduced training requirements and maintenance complexity across thousands of trucks. Caterpillar owned the owner-operator segment with engines that prioritized power and longevity. Independent drivers appreciated engines that could be understood and repaired without computer assistance. The mechanical simplicity meant that a knowledgeable operator could diagnose problems by sound, smell, and feel, skills that had been passed down through generations of diesel mechanics. Detroit drivers talked about fuel economy, diagnostic capabilities, and the smooth power delivery that made long hauls less fatiguing. The DDEC system became a point of pride for Detroit operators who learned to interpret the diagnostic codes and parameter readings that the system provided. Experienced drivers could predict maintenance needs weeks in advance by monitoring trends in oil pressure, coolant temperature, and fuel consumption. Caterpillar drivers talked about torque, durability, and the satisfaction of running an engine that could handle whatever they threw at it. The mechanical connection between driver and engine was visceral in ways that electronic systems couldn't match. Experienced Caterpillar operators could diagnose problems by listening to subtle changes in engine sound, feeling variations in power delivery, or noticing differences in exhaust smoke color. The rivalry reached its peak in the early 2000s, when both companies were producing engines that represented the pinnacle of pre-emissions diesel technology. The Series 60 had evolved into a 14-liter powerhouse that could produce over 500 horsepower while delivering fuel economy that kept fleets competitive. The C15 had become the gold standard for durability, with properly maintained examples accumulating over 1.5 million miles before requiring major service. Then came 2007 and everything changed. The Environmental Protection Agency's 2007 emissions standards required diesel engines to reduce nitrogen oxide emissions by 50% and particulate matter emissions by 90% compared to previous regulations. The technology required to meet these standards, exhaust gas recirculation, diesel particulate filters, and selective catalytic reduction, fundamentally altered the character of diesel engines. Detroit, with its history of electronic integration and continuous evolution, adapted. The company had been preparing for emissions regulations since the late 90s, developing after-treatment systems that could be integrated with DDEC controls to maintain performance while meeting environmental standards. The transition wasn't seamless. Early emissions-compliant Detroit engines suffered from reliability issues and increased complexity, but the company committed to solving the problems and supporting customers through the transition. Caterpillar struggled. The company's philosophy of mechanical simplicity and long-term durability was incompatible with the complex after-treatment systems required by 2007 regulations. Early ACERT engines designed to meet the new standards suffered from reliability problems that damaged Caterpillar's reputation for bulletproof durability. ACERT focused on in-cylinder combustion improvements, like twin turbos and variable valve timing, and avoided SCR and DEF, but still had to use diesel particulate filters with an aggressive exhaust burn regeneration system. That after-treatment setup, rather than the basic iron, became a major reliability headache. The approach was theoretically sound but practically problematic, creating engines that were sensitive to fuel quality, operating conditions, and maintenance procedures in ways that traditional Caterpillar engines had never been. The final blow came with the 2010 emissions standards, which required even more sophisticated after-treatment systems and tighter integration between engine and emissions controls. On June 12, 2008, Caterpillar announced that it would exit the on-highway truck engine market rather than develop 2010 compliant engines. The decision wasn't driven by technical inability. Caterpillar had the engineering resources to develop compliant engines. Instead, it reflected a strategic calculation that the on-highway market had evolved beyond the company's core competencies. Emissions regulations had made diesel engines into integrated systems that required constant electronic monitoring and intervention. The mechanical simplicity and long-term durability that defined Caterpillar's brand were no longer compatible with regulatory requirements. Caterpillar continued producing 2007 compliant engines through 2009, giving customers time to transition to other suppliers. The final C-15 rolled off the production line in 2010, ending 23 years of rivalry that had defined an era in American trucking. Detroit survived the transition, but the company that emerged was fundamentally different from the one that had started the rivalry. Under Daimler ownership, Detroit Diesel became fully integrated with Freightliner trucks, creating a vertically integrated system where engines, transmissions, and chassis were designed to work together. The current DD15 engine produces up to 560 horsepower from 14.8 liters of displacement, with fuel economy that exceeds anything from the pre-emissions era. But the DD15 is a different kind of engine than the Series 60 that started the rivalry. It requires diesel exhaust fluid, regenerates its particulate filter through controlled high-temperature burns, and monitors dozens of sensors to maintain emissions compliance. It's more efficient and cleaner than any previous Detroit engine, but it's also more complex and requires more sophisticated service procedures. The legacy of both companies lives on in unexpected places. Glider kit manufacturers still build new trucks around pre-emissions Caterpillar and Detroit engines, creating a thriving market for 3406E and C15 power plants that at the time could legally avoid modern emissions equipment, though later regulations limited this practice. Companies like Fitzgerald Glider Kits built entire businesses around installing rebuilt pre-emissions engines into new chassis, creating trucks that combined modern safety and comfort features with the reliability and simplicity of older power plants. Rural fleets, logging operations, and vocational haulers still seek out late-model trucks with pre-emissions Caterpillar engines, knowing that a properly maintained C15 will outlast multiple truck replacements. The rebuild market for these engines remains robust, with specialty shops that focus exclusively on Caterpillar power plants and maintain the institutional knowledge required to keep them running. Detroit's current position reflects the company's successful adaptation to regulatory reality. The DD15 dominates the integrated fleet market, where fuel economy and uptime matter more than mechanical simplicity. Freightliner's integration with Detroit Diesel creates operational advantages that independent engine suppliers can't match, from optimized aerodynamics to predictive maintenance systems that prevent failures before they occur. Today's trucking industry bears little resemblance to the world that created the Detroit Caterpillar rivalry. Engines are integrated systems that require specialized diagnostic equipment and factory-trained technicians. The mechanical simplicity that attracted drivers to Caterpillar engines is largely extinct, replaced by electronic controls that optimize performance in ways that human operators never could.